We've talked a little bit about the kinematics of simple harmonic motion. How does position relate to velocity? We've also talked about energy. What's been missing so far is thinking about forces. So we're going to bring a little bit of forces in, which relates back to acceleration. Then we're going to do something kind of crazy and mathematical. So first, let's think about a motion diagram that actually shows in one dimension what's happening. Now, the one challenge here is that the motion to the right and the motion to the left would actually be on top of each other. So to make this more clear, we've separated out the motion to the right on top and the motion to the left on bottom. So your equilibrium point is in the center. There, your acceleration is 0. Now, one of the ways to think through that is, again, if we think about a mass on a spring, this is your equilibrium point. There's no force there. And another way to think about it is that, again, in this sinusoidal motion, if we think about it starting here and moving to the right, it's slowing down, slowing down, slowing down, slowing down, stopping, turning around. This stopping and turning around, it has a maximum acceleration. Because, again, we could think about the derivative of cosine versus sine, where you have the 0 in one, you have maximum in the other. So we have maximum, it comes back, we have 0 in our velocity, not position, but 0 in velocity. The derivative of that, which is acceleration, will have a maximum. It then comes back, it's speeding up, but our acceleration is decreasing as it's speeding up. It has maximum speed here, and then it slows down again. So if it's going faster, 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 slower, 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 it seems like there's a place in the middle where it's momentarily constant, where acceleration is 0. So again, motion diagrams, we met these at the beginning of the class, and here's how we would think about it for this type of situation, simple harmonic motion. So let's talk more about acceleration. So we've already talked about how you can go from a plot of position to a plot of velocity, and then plot of acceleration would be the derivative of that. So we can directly go from position to acceleration, remembering that acceleration is the second derivative of position. And since our position plot is cosine, when you take one derivative, you get negative sign. When you take the second derivative, you get back to cosine, but now it's negative. However, you have to remember the chain rule. It's not just cosine of t, it's cosine of omega t. So when you take your first derivative, an omega pops out. When you take your second derivative, an omega pops out again. So acceleration, if we say our x, note that in this case we are using a phase constant phi naught equals 0, just for simplicity. So our initial equation looks like this, right? We have our cosine of omega t. We then look at acceleration. We now have negative omega squared a, which would give us our maximum acceleration times cosine omega t. So this is what position curve looks like. This is what acceleration curve looks like. So another way to think about this, and this is going to make sense if you think back to force, is that forces are, of course, mass times acceleration. So if we think about this as a block on a spring, would force be constant in time? No, our object is not actually staying in place. It's moving. And is force constant in position? No. For a spring force, it depends on where you are. So this is really important. You cannot use our Chapter 2 tools for analyzing simple harmonic motion. This is why it gets a whole chapter. Because when we dealt with kinematics back in Chapter 2, we usually simplified it to be constant acceleration. And when we talked about forces, we usually talked about constant forces. And those were two models that we used and then could use some really nice simple equations. Well, now we see that acceleration is not constant in time. And that's related to the fact that force is not constant in time. So that's why we need different tools to do this. And you shouldn't be going back to, for instance, x final equals x initial plus initial velocity times time plus 1/2 at squared. If you do that, you're going to get it wrong because that was only true for constant acceleration, and that's not the case now. So we know that this is our acceleration equation, and we know that our spring force in general is given by negative k, where k is our spring constant, times delta x, where delta x was our distance from equilibrium. Now, the only reason that I can say delta x becomes x is because we defined our equilibrium position to be 0. So remember, that is really important in our coordinate definition. So this first equation was really just coming from the fact that we said we knew what position was, and then we took the derivative. But we know what the force is, so this is kind of like having extra information and everything should agree. So what if instead we just said that I want to calculate what the acceleration is based on the force? Well, I divide by mass, and I have negative then 1 over mass, kx. But remember that the definition of acceleration is the second derivative of position. So even without using this, which originally came out of air, right? Like out of nowhere, I gave you this. This is now mathematically true based on Hooke's law and based on Newton's second law. So if we just want to use Hooke's law, which remember Hooke's law is just an ideal spring model, it's not really a law, and Newton's second law, which is actually a law, we get to this equation. So we should be able to use this equation to get back to the form that we were originally guessing. This is the idea of having an equation of motion, and this is a new idea in this class, so I'm going to take a little bit of time to go through this in 2 different sections. So the first thing to realize is that when I say that I have this equation where I have x is going to be a function of time, right? Over here I have the derivative of x with respect to t. So even though I just put x here as a variable, it's actually a function of time. This equation of motion defines the functional form that position must have. So when we made that plot before, again, I had pulled cosine of omega t out of thin air. I just told you that was true. Well, why? Well, because I said so. That's a terrible way to do physics. So instead of pulling it out of air, we can use the equation of motion to say what the functional form must be. This is actually differential equations. Solving an equation of motion is something you learn how to do in differential equations. My understanding is that you usually see a little bit of it in calculus 2. And obviously differential equations, which is Math 309, is not a prerequisite for intro physics. But frequently advanced math shows up in intro physics, and this is one of those times. So there's going to be a quick lesson on differential equations, and then we'll come back to equations of motion to really see what's going on here. You don't have to have mastery of differential equations to understand this, but it is helpful to understand why this gives us the form that we've been using up till now.